So here I'm discussing the homework assignment, and I want to remind you that, well, first, I could have made some errors in this. Just like the slide, there was a notational error. I don't know if you guys noticed. It had to do with my notation here, and it really just came to me, down to me having trouble in PowerPoint. But I'm not going to promise, so what I'm saying, I'm not going to promise that this is error-free. Just let me know if you see something. But I wanted to remind you what I would do in section 7.3 is write down these three main ideas. The first main idea is the first translation theorem, and I should have it here, so you'll see this in the textbook. What we're doing on these, you already know how to take Laplace transform of several functions. A, remember, is a constant. What we're doing is learning, okay, if you have a function and it's multiplied by an exponential term, then the Laplace transform will be the same as what you're doing, except it'll be evaluated at s minus a. So this e to the negative a, or I'm sorry, e to the at should represent a translation. And so that's why those are called the translation theorems. Now again, you will find these on the table in the back of your book. So we are looking at number 50 right now. So in the back of your book you have some translation theorems. I did skip a few of those. But number 50 is e to the at is times f of t. So that is what this is saying. I'm going to do an example or two. The notation that I didn't like how it was done in PowerPoint, but I kind of just gave up. The notation I was referring to is this notation. So what you're doing is you're taking the Laplace transform of f of t, but that will be a function in terms of s, so you're going to compose that with the function. You're going to compose that with s minus a. So what I mean by that is you'll substitute all of the s's for s minus a. And I'll work an example. Now when they give you a Laplace transform, because that's a one-to-one function or one-to-one transform, you know that you have that inverse. So the inverse of a function, if you can write that function completely in terms of s minus a, then you know it's e to the at times Laplace inverse of another Laplace transform, so you can evaluate that and find f of t. So I'll start back here. I wanted to go over these examples. The Laplace transform, so here you'll have a product of an exponential times cosine. You know how to take the Laplace transform of cosine of 2t. You will be doing that still, but since you have a product of times e to the 2t, then when you take that Laplace transform, you have a translation, and so you will need to substitute for all of the s's, s minus 2. You will get an expression that looks something like this. On the second example that I have here, this is the inverse Laplace transform. When you calculate, that reminds me of 1 over s squared, but since the function is written in terms of s minus 3, that tells me that I have a translation, and so to take care of that I will multiply the Laplace transform of 5 over s squared, or 1 over s squared, times e to the negative 3. That gives me this product. You could write this as 5t e to the negative 3t. So now I'm going to show you a few problems I worked from the book. Again, I think I checked these. If you do see an error, let me know. I only made sure that, I was doing some extra work to try to decide what to assign you all, and so there are a few extra problems on here. Number 9 was in your homework. On number 9 you need to expand that. I gave you number 9 because it included a couple different types of examples, so I didn't feel like you needed to do the first 4 if you did number 9. Number 9, because each of those terms will have an exponential, you will apply this theorem. So you'll notice one of those terms, if it's just a regular term like the last section, you'll just use our previous material. But if you have an exponential, you will substitute. So here you'll take the Laplace transform of cosine of 5t, but you'll substitute s minus 1 for s's. And here you will substitute s plus 4. On number 13, it is an inverse problem. You will have to complete the square. My apologies. We can't really avoid it. You'll have to complete the square. Once you notice that's a function completely in terms of s minus 3, you'll have 1 over s squared plus 1 left over. Well, that is simply the Laplace transform of sine of t, and this represents your translation. On number 17, I gave you number 17. You're not going to be able to avoid these forever either. So number 17, you had an s in the numerator. We don't have any transform that we can use for that. So I did a clever trick here. You'll get in the habit of this so much, and in Cal 2, if you didn't get in the habit of this, it's quite useful. So if you just had an s in the numerator, add and subtract 1 at the same time. You're not changing it, but that'll allow you to rip this apart so that you have 1 over s and 1 over s squared. Both of those were evaluated as plus 1. Now you'll be able to take the inverse Laplace transform, apply the inverse Laplace transform, and you'll get your outcome. So these are just a few, this to give you an idea of how this is working. Those are a couple example problems, and then I also wanted to show you, let's see, and I know I have an error here. Something about that is off. My A's are wrong. So I'm going to fix that before I send it to you guys. I have a negative in the wrong place. I'm going to try to edit this. I know that this will not be left with arrows, but to kind of just show you really quick, number 25, I'm going to attach that to this as well. So here, this is a DE I could have given you in chapter 4. Keep that in mind, but this is a new method. Change takes a little time to get used to, so before you hate this method, we're trying to practice it. Once we get very confident with this method, then we can decide what we do like and which methods we favor and which we do not. So again, keep in mind in chapter 7, I realize that we might not like the partial fraction decomposition, but we're still learning this method. Once you get more confident with it, then you'll be able to decide which method would be most appropriate in a specific case. So for number 25, I have applied the Laplace transform. You'll have to use partial fraction decomposition. This is one of the easiest ones I could give you since we're home, but I've left my work right here. I did get some fractions. You'll get fractions, and then once you rip that apart, you'll be able to apply the inverse Laplace transform. And I noticed that I left off the bottom of my problem. No, I did not. Okay, here we go. I just didn't scroll down, and then that'll give you your y of t, which is also in the back of the book if you can't read my handwriting. For this section, the second theorem is called the second translation theorem. Now, before you can understand this, you have to understand the unit step function. My last video, I didn't do a very good job in live time explaining that to you, but my last video I tried to detail that. All the unit step function is, if you could think of it as a light switch function, it tells you when to turn the function on or when to turn it off, and just like a light switch. If you have combinations, so if you have sums and differences, then you might have the light switch going on and off more than one time. That's how that would be affected That's how it would affect it. So the second translation theorem, once you understand the unit step function, if you have the product of a unit step function times a regular function, then our translation theorem simply tells us that this is a property. I talked a little more about this in the slides, a video that I sent out before, but right now I'm just going to show you a couple more examples. So here I have a Laplace transform of a product. It's 3t minus 15 and unit step t minus 5. Not exactly in the form of this theorem above, t minus a, t minus a. That means this function needs to be in terms of t minus 5. You're pretty much restricted, by the way. If you have a function of t, it must model this u, whatever u is composed with. So that means 3t minus 15. I wonder if I could write that in terms of t minus 5. Well, it just so happens that I could factor out a 3. I made it up, so that's why it's kind of easy. And then that gives us, so our f of t is 3t, and then u of t, so t minus 5. Because the function, this is f of t minus a times u of t minus a, then we are able to write e to the negative as. So a was 5. The 3 is just a constant, so you keep that. Remember, the Laplace transform is using an integral, so constant multiples just remain. And you have the Laplace transform of f of t. Well, f of t would be 3t. So I could have left this as 3t or t. The Laplace transform of t is 1 over s squared. 3 again is your constant. E to the negative 5s is because of your unit step factor. So that is your first example. Another example, this one's trickier. If you got something like this, 2t times a unit step function, it doesn't have this form. That doesn't mean you can't manipulate it so that it does though. So you'll notice in this example what I did is it didn't have that form. So I decided to force it. I need to write 2t in terms of t minus 5. I can't change the overall value, but I can rewrite the form. It's like calling me Nick versus Nikki or Miss Nikki. So what I did here is 2t I rewrote as 2t minus 10 plus 10. And I kept the first part, 2 times the quantity t minus 5 times the unit step function, and then plus 10 unit step function of t minus 5. So pause this video. This inside the brackets is the same as what I had up here. Now that I've done that, I have two functions, so two terms here. This f of t would be 2t, so I have 2. The exponential is because of the unit step term, the product, so it's because of this theorem. And then I just have to remember to take Laplace transform of t, the function f of t. 10 unit step function, so if f is simply equal to 1, then this is simply e to the negative as. And that I didn't write that on this, it is in the back of your book as well though, and you can think about just, okay, what would happen if you took the Laplace transform of u? Well, it would be 0 before a and 1 after a, so the unit step function is 1 after a, so the Laplace transform would be 1 over s, but because we have a unit step function, because that interval where we turn that on and off, we get an e to the negative s. So the Laplace transform of the unit step function term will give me this, and then so this is from my first term, and then the 10 unit step function, that is from this term. And I could have factored that or made it more fancy, but I left it there. So then I ask you all to do 37, which is similar to my first example. It's already in the form. 39 is more similar to the second example. 45 is the inverse. So here, if you ever have a Laplace inverse and you have an e to the negative s, you know you're going to get a unit step function. So when I look at this, I kind of just ignore that for a minute, and I think 1 over s squared plus 1 is what I need to focus on. Well, I recognize that as sine, but I'm going to have to replace the t with a t minus pi because of the exponential, and multiply by a unit step function evaluated at t minus pi because of that. Now on this problem, I did want to show you on 45. I think you all would have done fine on that part, but to get the answer in the back of the book, they're simply using some trig. So they use the sum, or they use the difference formula for sine, so they expanded this just using trig, which isn't bad practice. Hopefully you had those memorized from your trig class. And once you expand that, well, some terms cancel so that you get the answer in the back of the book. So be really careful. 45 is where if students are just using the answers in the back of the book, yeah, you can write that answer, but you might not really understand why. So take a look at my 45 and that trig. 49 through 54, I did not want to stress you out. These are matching problems. I tried to write some answers why. I would not, it's totally fine if you do use the answers in the back of the book to help you understand that. The whole idea about 49 through 54 is to help you understand how the unit step function affects the curve, affects the graph. And so once you have a handle on that, the reason you need to know how to do that is because you would never know how to apply this idea to a differential equation such as 65 unless you can write a function in terms of its unit step function. So if you ever have a piecewise function and you are asked to solve a differential equation, well, you're going to need a Laplace transform. None of our other methods were able to evaluate cases like that. So what I've done here, in this example, I recommend going through slowly. I've taken f of t and I've rewritten that. So they gave me a piecewise function. I wrote it as a difference. I have t minus t times a unit step function. Take some time to really try to understand that. Don't just write it down and use it. If you're using Slater, don't just take that without trying to understand it. So that's why I had you do the matching problems. And then once you have rewritten f of t, then you will be able to apply the Laplace transform, plug in your initial value, and yes, you will have some partial fraction decomposition. You can even see I had some erasing. I had some trouble on this one. Practice this. It's really, yes, there is technology, but Laplace transforms, you're not going to be able to avoid partial fraction decomposition, and this really is some of the easier ones. And so remember, if you have linear terms, you can use the cover-up method if they're to the first degree, not for squared terms. And the cover-up method just doesn't solve for all of your constants on these, and so that's why it took a little work. This one, it does. This is a piece of cake over here, but over there it doesn't. I remember when I was working this, I did have a negative out of place over here on the right somewhere, and I think I fixed that, but if you notice it again, there is a negative that I remember I lost track of a couple times, so you might see that, and last night around midnight I gave up looking for it. Okay, so what I've done here is I've found all my constants. I grouped some terms together. Right here is the work that I think you might want to pay attention to help you understand this. So the inverse Laplace transform of this term, you'll notice you have a 1/2 s squared. No, this one is a piece of cake, but 1/2 s squared e to the negative s. So this term is what I wrote down here, and what I tried to do is kind of, because that e to the negative s, I tried to remind you, okay, that's going to represent a unit step function. And then because it's 1 over 2s squared, I have the 1/2. The s squared tells me the inverse of that would be t, so I'll evaluate it at t minus 1, and that would be that term. You'll also notice you have a 1/4 over s e to the negative s and a negative 1/2 1 over s e to the negative s. So I put those together and took the inverse Laplace transform. Those will just be a constant times the unit step function. The other term that you'll have to deal with is this 1/4 e to the negative s over s plus 2, and this one. I put those together and took the inverse right here. Really spend some time trying to understand that. I realized that this problem could take a while. I'm not gonna lie, this problem took me a while, but I tried to only give you one of these, and I am giving you my work, but really spend time and try to understand it. So that's the goal. Otherwise, we'd have to do many more so that we really understood it. But if you'll just spend some time understanding this, I don't want to give you extra busy work. Once you finish that, the answer, of course, is in the back of the book. Mine is in a slightly different order, but all my terms appear. Again, I had some trouble with my partial fraction decomposition right here, but I think that's fixed. And I make errors all the time. You guys, the big ideas here are what are important. And I try to never mark you off for little algebraic things, because some of this, it does take quite a bit of time and a lot of algebra and calculus. So as long as you know these main ideas, you need to understand the partial fraction decomposition, and then what we're trying to focus on in this section are the two new theorems and understanding the unit step function. Thank you. Best of luck.